and most likely in the middle. So, maybe most likely it's kind of skewed over here or something. So you need to know some of these, at least some of these you have to choose one, or you see a process, or you plot your times or your failure rates or something, and you say, well, it kind of looks a histogram. The histogram doesn't look normal. Well, what is it? Well, maybe it's log normal and uniform or something like that. So exponential is inner arrival times. So here's what its density looks like. Yeah. Now in this case, this is not its density. This is actually its probability. I'm sorry, 1 minus u minus lambda x. And again, where did this come from? Yeah, it came from some fairly sophisticated math relative to the distribution, which we don't need to do. We just need to know that, hey, here's an example. Let's say we're a service counter at a bank, or we're Baskin Robbins, and we find out that people arrive at a rate of 15 per hour. So that would not be that hard of a number to come up with, right? If you're a laundromat or you're something, you're going to think about buying this, you're going to just go and count, find out what the rate is. And now you can say, okay, I've got my key number. That's the lambda in here. I've got my key number. Now let me just model this as an exponential distribution, and now I can answer this question. So let's see, what is the probability that the arrival time between two customers is less than 3 minutes? Well, why would you ask yourself this? Well, maybe I need to know how many staff to get, right? Or how many pencils to give them because they're going to run out or something. I need to know. What's the probability this is going to happen? Well, and off the seat of your pants, you can kind of figure it out, right? Let's see, 15 per hour sort of says, well, that's 1 every 4 minutes, right? Yeah. So what's the probability that I get two customers that are set apart by 3 minutes? Well, it's not going to be 0, right? If I expect them 1 every 4 minutes, it's not going to be completely unusual that I get 1 every 3 minutes. So the probability is not going to be 1%, but it's also not going to be 99%, right? If we expect 1 every 4 minutes, 1 every 3 minutes, somewhat unusual. Well, let's plug it in. So 1 minus e to the minus 15 times 0.05. Why did where did that come from? Let's see, 15 was the number of arrivals per hour, and 3 minutes is what? Well, 1 is 0.05 of an hour, right? It's 1/20th of an hour. So be careful if you do use this. Make sure that if this is hours, that's hours. This for minutes. You could put that minutes and that minutes to be fine too. That'd be okay. But anyway, so the probability is 53%. That's probably right. Yeah. If we think people are going to come every 4 minutes, there's a 52% chance that they'll come every 3 minutes. And you can see, what's the probability that they're going to come instantaneously? Well, e to the 0 is 1, 1 minus 1 is 0. Oh yeah, okay. So with this process, they're not going to come instantaneously. And what's the probability they're going to come with a separation of 1 minute? Well, it's going to get smaller, right? So this is going to be smaller. This is going to make that number bigger. 1 minus a bigger number is going to make that smaller. You can play with it. You can see it kind of makes sense. So really, this is a good distribution. You can see how you could use this in a model with measuring one thing. And you can do it at different times. You can say, no, wait a minute. What? This is lunch. What about at 3 o'clock when nobody comes to the bank? Yeah, that's true. With these simulation modeling softwares, you can have that happen. You could have your distribution be time dependent, which might be useful. All right, so we're almost done, and then we take a break and then do some problems. Here's the exponential distribution in Excel. Isn't it funny? We've gone through the normal distribution, we've gone to the uniform distribution. Now it's shown you one piece of Excel. Then we get to this one, which is probably the least useful of all these 3 distributions. I'm going to show it to you. I mean, the others are in the book. I'll show you the others. I didn't even look this one up. I'm like, I don't care. They're hard. They probably will never use this one. It's important to know. So we've looked at these 3 distributions. We've shown how you can find probabilities using formulas and tables with them. So,
you mentioned the modeling software a few times last semester too. How long would it take to do a simple model of, like the example you just said, at lunch or 3 o'clock?
Not long at all, really.
Is that something that you could show us?
I could show you how to do it.
It's
easy. Literally, if you don't want to get too much involved, and you would say you want to have customers showing up, like a bank. Let's say we're going to have some customers showing up, and let's say we have 3 tellers, and we want to see You know, if customers come at this rate, how many get through and how many pile up in the line? That would be, I could set that model up for you in like 5 minutes.
Right.
Now, you recognize there's some unsophisticatedness in that model, like I'm not letting the intervals vary over time yet. Although they will be random. You know, if we set up an exponential distribution, you'll see the simulated tellers, customers will show up at 2 minutes, 3 minutes, 5 minutes type thing. I could easily let the service time vary randomly. So that wouldn't add to the 5 minutes, but I'm not allowing tellers to come and go. So if you ask me to say, well, let's set it up to where we have 2 tellers at between 10 and 11, and 3 between 11 and 12, and 5 between 12 and 1, then that might take me an hour to set up. Because, you know, I've got to be a little bit more sophisticated to, you know, make the model accommodate different, but you're still not talking very long.
Yeah,
No.
well, I mean, I don't know, maybe if everybody's interested, we can do like a short one just to kind of see.
I could show you, I could bring it in. I've got some software at home that does it. It's an old version, but yeah, because it's simple, it's easy, and if you guys want to do that for one of your capstone projects, you get a lot of mileage out of it. Because you can answer some pretty cool questions and make some nice plots and, you know, come up with some decent conclusions pretty fast. You know, it's a useful tool, especially for industrial engineers. It's one of the industrial engineering core tools in your pocket. So everybody ought to at least see it. So yeah, I'll bring it in. I'll bring you the one. And you can do it. I can show you how to do it in Excel too. It's not as pretty. You know, the simulation softwares, they have nice animations. And so if I want to do a bank, I can have actually little people, you know, animated people show up. And they can stand in the line. And I can, you know, and that's real pretty if you're showing it to management, but it doesn't do anything to the math. The math's the same. And so I can show you how to do something like that in Excel. If you need to do that, you can do both. So maybe I'll try that. I'll try to set something up, because that sounds useful. It's a useful tool, especially for us in the manufacturing world. And don't just restrict yourself. Don't close your mind and say it's got to be people carrying parts to a machine, and the machine being, you know, a bank is an obvious, easy thing, but there's many things you could model that way. You could model rules, you know, and you can model each of the things that occur can have resources associated with them. So they can and cannot occur. Like say it's a manufacturing process, you got to have some wrenches and screwdrivers. Well, if they're not there, it won't happen, and jobs can wait. Or jobs can wait on particular parts in these software. And that's all, that kind of logic is real easy to program because they're set up for that. So something even decently sophisticated like that in a day or so, we can set up a good model and get you some good answers. You could look at what happens if I lose 2 of my wrenches? You know, how does that slow my process down? Or maybe it's not wrenches, maybe it's rules, like a 2-man rule. If you don't have 2 men there, it doesn't go on. So production stops for a while until you get 2 people free. And so you can model things like that very easily. So yeah, I'll show you, because I do think it's a useful tool. So they have this little topic in there. It's actually in the book. I'm going to fly through this. I don't have any clue why you would be excited about approximating a discrete distribution with a continuous one when we can use Excel. But okay, there's about 5 view graphs I'll show you. So what they're trying to do, remember the binomial distribution last time was one that was discrete, 4, 5, 6, 7, and the normal distribution is not, it's continuous. Well, gee, you know, maybe we can kind of fit this normal distribution like from 2.5 to 3.5 and let that be the probability for a binomial distribution of 3. Okay, would that work? Well, yeah, it would work if we have a binomial distribution that's got that pi parameter in it equal to 50%. Remember how that was when we played with it. If you had the pi parameter equal to 25%, it's skewed to the left. If it's 75, it's skewed to the right. So if it's one that's got an equal probability of being in the middle there, you know, if it was equally 1, 2, 3, 4, 5, and the mean was at 3 there, then you could use the normal distribution. Okay, well, that's all you need to know. That's it, right? So here's their example. They've got a discrete distribution. So what's the probability of 4? Well, let's use the normal distribution between 3 and 5. And so, hey, you can do that. Let's see, closer pi is to 5. And there's the normal approximation of binomial distribution. Yeah, using this. I think they introduced this here because you'll wind up seeing formulas like this when we get ready to do some of the inferencing. Again, I'm not interested in you knowing this topic. Your takeaway for this is, yeah, I guess I could approximate a discrete distribution with a continuous one if I had to for some strange reason, and maybe, 5 years from now when you're in your PhD program and you get some class and they do that, you can get excited about it then. I don't think it has much applicability here. Yeah. So there, it's. Yeah. So here's the actual numerical example they're doing. Yeah. Anyway, we'll get through that. Yeah. Okay. So take a little break and get in the bathroom and get a drink, and then we'll do some problems, because I think it's critical to do problems out of this chapter to consolidate what you've learned about these probabilities and how to use them, because we will use them again. And I think you'll see it very clearly when we do the problems, I think. Not when we do them again.
That simulation software you have called SAT.
No, the one that I used, that Y12 used, Extend Sim. Yeah. There's a million of them. There's Simulate, there's Simio, there's.
I've got to use it in my capstone. So.
You got to use one of those?
Yeah, I have to do a major simulation like that.
And Extend, since you're in school, UT has it, but you have to sort of ask permission to use it because the business school has it. I don't think it's hard. Maybe I should pursue that because I'd like to get it again. I have an old version that's like 10 years old. But we can buy it as students for $50. And the only problem is it's like any student software, it expires after a while, and you're limited to like, I don't know, 100 blocks or something, which could be a problem if you've got to have a huge simulation.
It's probably going to be huge.
Yeah, because it doesn't take long to get over 100 blocks, because you've got some logic. Yeah.
I don't know if you had a second, we could talk about it.
Yeah, we can. Yeah.
Okay, so what I've got is, this is some detail, it's not a pretty chart, but it's detail.
Yeah, I don't know how complicated it really wants it, but that part's already done.
You can just see the system here, location of the failure.
Yeah.
That's what you see that.
Yeah.
We've got something there. You think had to replace that manufacturing? Took it to go to a different.
I haven't really seen about that much. I was gonna try to.
Well, that's what we suspect. The new detectors causing detectors to drift sooner than the older detectors.
Yeah, I was gonna wait till we kind of got a full
Each
bit.
one.
Well, I was gonna wait till I.
6 or 7 in the last year, let's say.
Oh, yeah.
So what I've got, this is kind of what I was thinking, right now I've got that many deployed in the field, so they didn't have to do it.
But I'm waiting on this one, Dr. Strong.
At any time that they can do that operation. We keep a stock total inventory about 50. 32. I've got 2 right now in the lab that
I know that that's
successfully counted.
We're sitting there ready to get there.
They're ready to go, but you have to change these out. Change them on a 12-month interval. They're required to calibrate their curve.
And then we're gonna go to
Our fear is, as we said earlier,
We'll run out of these.
we're gonna run out of these. The majority of those failures.
I sent that back.
So pull it out, you bring it in, you can't calibrate it, now you're in trouble.
Right, so if we don't have that stock that we use to rotate out, then we're going to bounce. Probably
Did she send you something like just?
change out. If this is on, if we can only have that.
Me too.
We're gonna be.
Be
able to.
This would be great for simulation ball. We can play with that.
Okay, so that was gonna happen.
We'll plan on Monday, Tuesday.
That's fine.
Yeah, we're doing
Like to show people, this is what we are, based on the information, this is how much failure we're expecting to see during this time. And that's the basis, while it's probably we'll accelerate change before we're doing on a 12-month basis. Now, get creative and do it on
We can easily simulate that, we can easily simulate that. But let's show when the problem occurs. Let's show randomly, like we have sort of this, like a crank failure rate.
I think that Carlo was talking to Ronnie about somebody expressed concern about that.
Count how many times. It doesn't have to stop. You can just say, well, look, over the year, 5 times we ran out of them. God. And you can show that if you double your.
And he's not, I don't think they should teach me to test. From what I remember trying to learn it was, you had to think about it just from sort of perspective. And you had to really emphasize that, because you'd say, this isn't something I would practically do. But this is something that they think needs to happen. And he had even third time, like, change
I'm
back. You're not, you have to get all these approvals before you're allowed to actually change your scope.
I'd be like,
Basis.
no. No,
Already. He's really teaching it that
So,
way.
if I,
Those prep courses, that's all they do, is teach you, they don't want you to do something, they just want to teach you how to pass the
knowing
test.
where all this software, what's the easiest to teach? Do you have a copy?
I do.
But I'll be like.
So maybe we can meet up with Jack Case or New Hope or
Yeah, I can do it. Let's get new home.
yeah, if you want me to come to the plant, that's fine.
Can I be my backup? Used to you couldn't.
Yeah, they can bring it.
Can now, used to you
Bring
couldn't.
laptops in the New Hope.
Into the lobby part, right?
Yeah.
Okay. Yeah, I'll bring it, I'll
I
bring
mean,
it.
you can bring cell phones, we can't have cell phones, but they can.
Yeah, that and then.
I'll bring it, and we'll.
We have a hard time getting a pager.
We're not thinking between on how to do it, if I can do it in Excel. Because I think I
Are
can.
there any other numbers you can think of that I would need?
I can get you that.
This
Last column right here, I'll have that filled in, I've got it.
And do you have any kind of, any information on the failure rate, sort of?
Yeah, what I was thinking compared to is I know from his report, the ones that have failed, but I also want to put that over the total number of units. So if we, for instance, if we had 6 failures in that year, but we calibrated 6 total, or
He's going on
36
his annual
total,
Underwood.
then, you know, the issues over 36 and you failed.
Failure rate, yeah, exactly.
So.
Do you now want to know how you got the?
Yeah, get all
Pull
of
that.
those, and get it both ways, don't, if you have 6 and 36, bring both those numbers, because we may wind up doing it a different way, and don't just tell me 1/6. Yeah, give me both, because both have
Right,
value, yeah,
definitely.
yeah.
I agree.
Yeah, no, this could be good.
I agree when you find out that
a lot
somebody
of
got a
fun,
job,
you know?
they go on fishing trips with somebody else.
Well, it's fun for you.
Bother
For me, because I'll have to deal with all the people crying about it, but.
Yeah, that's true.
At least I'll have good information for them.
We'll grab a drink too, real quick, and then. I think, as you see these examples, I think it'll be really clear. I think. How about I didn't disturb you guys when we were talking back here? I know one of you guys had to shut it up, sorry. When we were talking before class.
no.
Too much noise.
He's just showing you all the actual steps. The actual answers are 13, 14, 15, 16.
You could have sat in my chair.
I was looking at the. I didn't.
Didn't want to touch anything that you had.
I wanted to make sure he got.
Joe already found
I saw it. It's tempting.
it. And we all were like, I don't know how to say it.
Yeah, I saw it. I was thinking the same thing.
Yeah, that's why.
I think it's gonna be driving this one.
To be honest with you, I don't think that everybody.
I know. How much can you take?
I need that to be the first class, because that's the one I have to focus on.
Sonny's not giving that talk, you know, Annie.
Maybe it'll next semester with his new class.
Oh, that's
Dude, they're like, I looked up my property and that was really small. Because we have that already. Like 20.
yeah, they don't want to come in.
Yes.
Just to have this program.
Yes, exactly.
Yeah,
Because it was kind of ludicrous. I mean, just the thing.
Here's an illustration of the normal distribution from a kind of a funny perspective, but it's people, right? So there's not so many short people, you know, so the probability density is low for the short people. Most people are average height, right? So it's the density is higher here, and then there's a few Shaquille O'Neals and that sort of thing, big guys out here. And if you don't believe it, there's an even more humorous picture down here below. Look at these. These are some recruits at a military school in 1914, and they've got them arranged by height. And it, you know, just by arranging them by height, they made a normal distribution. You can see. You know, that's the guy. He's 14, and this guy's 6'2". And they've just piled them up in lines based every inch. Yeah. So you can see how that kind of thing works. How they were, you know. Go stand in a cemetery 100 years ago, you know. Everybody didn't have as good a nutrition, right?
I'd say
But that might give you a feel for the normal distribution. What it's trying to do, you know, it's looking at the distribution of something that varies. You know, in this fashion, like we said, that has most of them kind of concentrated around the middle. You know, what kind of processes we've talked about, you know, samples, height, length of appendages, things like that. So that's pretty humorous, really.
Not only is he the carbon on the thing, he didn't even have people beside
It was hard for me to find anything much humorous about a normal distribution. This is a log normal distribution. No, we talked about, we had normal, exponential, uniform, and this is another one. There's others too. There's beta and things like that. But you see this the one characteristic about this, it even kind of sounds like normal too. You know, log normal. It's very similar to the normal, except it's got a tail over here, and you can also flip it and have the tail go the other way. This is the one we said is salaries or house price. I think these are engineering salaries, right, by degree. Bachelor's, master's, doctorate. So it shows you don't get a PhD because it doesn't make any difference. It doesn't. And especially if you say that it took 5 or 6 years to get it at the front of your you know, of your career, and you still wait $200,000 worth of 5 years of work or something. You know, it's just like, yeah, you know, you're way out here. It's kind of funny. Here's some different log normal distributions, just like the different normal ones. And here's some things that you might be able to use it for. So, you know, you might ask yourself, I've got some process, which distribution should I use? You can search this kind of stuff on the internet. You know, human behavior, length of comments posted on the internet discussion forums. Follow that, okay? Dwell time on online articles follows that. And you can see why. You know, this is the kind of thing where something's around and normal, but then sometimes people hang on for a long time, you know, or sometimes people write a long thing on the discussion forum, or the last one I made in yellow. Income of 97 to 99% of the population is distributed log normally. Okay, so if we were going to do some sort of model of income, we'd probably better off modeling this log normal than normal. But if we did that normal probability plot of income, it wouldn't come out as a straight line.
What
So
was
it's-
log normal again?
It's that picture you saw up there. So see, it's just instead of symmetrical, it's got this tail.
Ah.
Yeah. So you know, instead of being right around this average, good and symmetrical, no, it's got these weird long outliers like income would have, or house prices. You know, it's just some weird. And again, by adjusting these parameters, you could actually flip it around the other way. So if you had some small ones for whatever reason, I can't think of offhand something that might follow that, just because I haven't, all of mine have been kind of this way when I've seen them. But anyway, just another distribution they didn't mention in the book, but if you do simulation modeling, you'll see that would show up. So let me work a few problems because I think it'll help clear this up, I think. So the first problem that I was going to work for you is problem 6.4. With it being that low of a number, you can imagine it's a simple problem. And it doesn't even have any setup or anything. It just says, oh, let's just play with the z distribution for a minute and try to understand the z distribution. And so and the Z distribution, remember, that's our standardized normal distribution. We took the normal distribution and crammed it all down to where it has a mean of 0 and a standard deviation of 1. And so 6.4 is just asking a bunch of random questions about the Z distribution. So the first one is, hey, what's the probability that Z is greater than 1.08? So first thing I'm going to draw all these for you. Yeah, here they are. Okay, yeah. I'm going to draw some of these for you, so we can, because I think if you see them, you'll say, oh, I see what I'm asking. So here's our Z, and here's our probability axis up here. And remember, our normal distribution is symmetrical, looks like that, and it's 0, and that's the mean, and the standard deviation is 1. So now this question is, what's the probability that Z is greater than 1.08? So that's somewhere out here, right? 1.08. So they're asking, what is this? See what they're asking? And again, why are you asking that? Because we've related this to some other process, perhaps, like the download time, the 18 seconds, the 18.6 seconds, or the 18 seconds mean with the standard deviation of 5. But right now, this problem, they're not even setting up a scenario. They're just saying, hey, what's the probability? So what's the probability that Z is greater than 1.08? Now, we can take that density function, the e to the minus something, we can integrate it from minus infinity to 1.08 if we want to, or hey, we can go to that table. I vote we go to the table. So hey, let's do that and just show real quick what it is. So here's our table. This is table E2 in the back of the book. Again, remember how to read it? Here's the 1.0. This is 1.00, 1.01. So make sure I get things lined up right. I'm on the right line, yeah. 0.8599. Okay, now, but now I've not quite got the right answer yet, have I? Let's see. Because that's the probability from this side, right? From the table. Remember, the table is always giving you from minus infinity up to that Z. Yeah. So that table is telling me 1.08. It's 8599. Okay, so that's it. So how do we figure that? Well, the whole thing is 1. So the probability is 1 minus 14. Let's see. Getting on the other one. So we'll have to do the math there. Now, so I had to have a little bit of intuition. Maybe, you knew that it had to be, this is 50% here, this little red blob had to be kind of small, right? It had to be, 14%. Yeah, it wasn't going to be teeny tiny because we're one standard deviation away here. So, I think you got, does that make sense how you calculate that? And how we're looking at this side because we're asking greater. Okay, let's see. Oh, they're going to ask some less ones too. So I've got in my book, you can't tell in here, this is red, corresponds to red. So you can see it when you download it. Yeah, what's this down here? This is me working in an Excel for you, in case you don't want to go to that table. All right, so in Excel, norm dist is table E2, okay? So if I put in norm dist and I put in 1.08, 01, true, I'm gonna get that. Now, what am I putting in? This is the Z, this is the mean, and this is the standard deviation. So I could actually put in whatever normal distribution I want. Okay, I think the true. What does the true mean? The true says give you this whole cumulative area, not just the density function, not just the height, but give you the area. That's what it says. All right, so you can see I got 1 minus that gives you the same number. So now let's do the next one. What's the probability that z is less than 0.21? So now they kind of went on the other side. So you got over here, we're down here at minus 0.21, and they want to know what's the probability that z is less than minus 0.21. Okay, so they're asking that. So let's see. I probably shouldn't have drawn it so, draw it so far away. Let me draw it more accurately. It's really more close here, right? If that's 1, we'll draw it better. It'll make our answer look a little better. Okay. So, hey, that's just straight out of the table. If we just go straight to the table. Okay, now, remember we're on the plus side here. Let's go to the minus side. There we go. Ah, that's why I had that other table. I had another table that wasn't in your book, so you could see the top and the bottom. It had the numbers on the bottom. Anyway, I'll show you. So there's a minus sign there. Minus 0.20 minus 0.21. 4168. All right, let's see if that's. And then see, we don't even have to do any math here. That's just straight there. Yeah. 4168. So what that says is this area is 41.68%. Does that make sense? Yeah, because below the line it was 50%. But we're just kind of barely below the line. That's why I redrew it. So this is 42%. Yeah, okay. So here, straight out of the table. Or if we did it in Excel, I don't have a 1 minus, right? I have norm disk, minus 0.21, 0, 1, true. Oh, there it is, 4168. All right, now the next question is, what, I'll redraw it maybe, what's the probability that we're between here? Minus 1.96 and minus 0.21. So they want to know this time, what's this probability? Remember the table's not going to give us that. It's not going to give us a difference. The table's going to give us this little green one, and then it's going to give us what are the colors? It's going to give us this entire one, right? That's the one we just got, right? The less than 0.21. Right, mathematically. So now we're going to say. So we're asking ourselves, what's the probability? Z is bigger than that, and less than that. Okay, well that's the probability that Z is less than minus 0.21 minus the probability that Z is less than minus 1.96. And you see why that in their little procedural thing, they said, draw a picture first. Because it does seem to help. After you get used to it, you can probably do it in your head. You can probably do this in your head after you get used to it. But if you just draw a picture, you're liable to make a lot less mistakes. And plus, we can get an idea. Hey, we know that this whole thing I just circled, we already got the answer to that, right? This first part, this equals 0.4168 minus something over here. Well, we know this is going to be pretty tiny. And so we can already get an idea of what our answer should be. And you can kind of get an idea, too, of the picture. And how do we get that? Minus 1.96. Well, let's go to the table again. As we go over here. Yeah, and there we are. And let's see, we're not. Oh, here we are. Yeah, we're going to see. Maybe I can roll it up and we can actually see the top this time. Yeah. Minus 1.90. 1, 2, 3, 4, 5, 6. Yeah. 0.02. Okay. So now this whole difference is something. Now, there's a whole difference there. 18. That's right, yeah. 39. That's 42%. In fact, this itty-bitty thing, yeah, that's 39%. Now, truth is, I could have written this down from my head without looking at the table. Is it because I'm a genius? No. This is what I was telling you. They're being subtle with this little number here. That's one that's going to show up when we start asking about the 5% confidence interval. Because it's 2.5% on one side, 2.5% on the other. So you actually, this little z of minus 1.96, by the time you're in this class, you will recognize that too, by the time you're done with this class. Same with the, there's 1.68 or something in one of the other, 1.65, one of the other problems. And so there's a couple of these things that you'll start to recognize, and they're subtly sneaking this one in here, even though it has nothing to do with this problem, and they finally picked that. But, so anyway, so yeah, so the probability that it's between these two values is 39%. Yeah, that's good. Here's the XL. Norm dis minus 0.21 minus norm dis minus 0.6. And if you got it backwards, you just get a negative number and say, oh, wait a minute, I subtracted the wrong one from it. The probability can't be negative. Don't do that kind of thing. Okay, and so now the last one is the backwards problem, right? So the last one, let me read it so you'll know how it would say. Right, see, the last one says, what is the value of z if only 15.87% of all possible values of z are larger? Oh, okay. So let's see. What are they saying? Okay, so we still got our standardized normal distribution. F of z. It's a lot worse. Here we go. So we're wanting to know, hey, what's this z star out here, where this area is 15.87. No, that's what they said, right? 15.87. Yeah. Now, why did they pick 15.87? Well, you know why. It's going to be a number that shows up in the table. Thankfully, if we're using Excel, we could have picked 15, and 15 probably not in the table. So again, this is that question. What's the cutoff speed below which 85% of our videos will download? Or this is the test grades or where I've got the top 16% of the class, that sort of thing. These guys will be A's or something. These girls, guys will be right. So let's see. So how do we answer this? So we've got, what's the probability that z is bigger than z star equals 0.1587? Well, first, remember, we're working with this clunky, goofy, silly table, and it's only going to give us this, right? Remember, it always gives us that. So we need to know what that is. Well, what's that? That's 1 minus 0.1587. So that's, what I got right up there for us. That's 8413. 8413. So asking this question is the same as saying, hey, what's the probability that z is less than z star is equal to 0.8413, right? Same question. And why am I asking the green question again? Because the table only has the green answers. The table doesn't have the red answers, so I got to ask the green question. So let's go look at the green question table here. So let's see. And we know it's on the positive side of the world, right? Because we got 84%. This green blob's 84%. We know it's on the, this is positive, and this is the negative. Remember, this is a mean 0 here. That's plus step deviation. So let's go find it. 84, 13. Oh, there it is. Yeah, 1. Z is 1. Okay, not Z. Z star. It's 1. Alrighty. You see how I found it? I just looked for it here. And and if they told us 84.15, well, we could have just picked that anyway. There's 1 here. That's close enough. Now let's finish the problem. We're not quite done. Well, yeah, we are done, I guess, because they wanted to know Z, right? Yeah. Yeah. Now, could I have used the table without calculating the green? If you think about it, this distribution is symmetrical, right? So the answer that has 0.1587 here is the same answer, except it's just on the negative side, isn't it? So if you can visualize that, we could have gone to the table and not had to subtract 1, not that that's saving a huge set of steps. But if we went up here and said, look, 0.1587 on that side corresponds to -1. This is z star, if you will, equal to -1. So therefore, we know that the 0.1587 over here is z star equal 1. I wouldn't recommend thinking that way, but I thought I'd show you in case that opens your eyes, or start thinking, oh yeah, it's symmetrical, right? I could have done that. No, yeah, I could have cheated like that. But I think the green approach is better because it is the right way to do things. Now, let's see. And here it is in Excel. I put in 1 minus 0.1587. Notice that it's the inverse. Because the distribution gives me the probability. The inverse gives me the z that goes along with the probability. And if you don't remember, just play with it. Or start typing it in, because it tells you when you start typing it in Excel, you start typing this in, the first thing it says is what's the z value. You start typing this in, the first thing it asks for is what's the probability, the cheap thing that pops up. You can't remember. And if you can't remember, because I can't remember when I stay away from it for a while, just Google. Start typing norm this in Google, it'll pop up norm this in Excel, it'll show you in 3 seconds. So even if you can't remember, it's going to be at your fingertips real quick. All right, so that's 6.4. Now, can you guess what 6.10 is going to be? 6.10 is the exact same problem. I mean, not the exact same, but an exactly similar problem, except now instead of working in the Z world, they said, well, let's do this problem in the X world and show you how to flip-flop back and forth. Because remember, Z is our standard normal distribution, but the X world is your distribution, the one with the 18-second mean and the 5-second standard deviation, or the 3-day mean and the 20-minute standard deviation. So we're going to ask the same set of questions. I won't flip back and forth between the table maybe as much. But what this is a test. Yeah, it's normally distributed test scores. The mean is 73 and the standard deviation is 8. So it's a test you might have in a class like this. Okay, so the first question is, if you got a 91, what's the probability that a score of 91, what percentage of the kids is how you're going to ask it? I have a score less than a 91. So let's see. So let's draw that way. So there, yeah. So here. So the first question is, so we've got, I'm going to write that. So we've got a test. Okay, the mean is 73 and the standard deviation is 8. And our first question we're going to ask is, here's our distribution. And now I guess, I'll draw it like the standard anyway, just because it will look that way. Our mean is 73, standard deviation 8. And our question is, what happens as we put it in the right spot? What happens here, 91, right? Okay. So now we're going to ask, what percentage of the students have got a score less than or equal to 91? So this is what we're doing. What's the probability that my score is less than 91? Okay. Oh, well, yeah, how can we do that? Well, we could put that straight into Excel using the standard distribution, or we could plug it straight in, or we could use these tables. Oh, that's the same as asking what's the probability that Z is less than or equal to what? 91 minus 73 over 8. See, I use that normalization formula, right? X minus V over sigma. Okay, all right. So that's the probability. What I calculated for myself here. Yeah. What's the probability that Z is less than 2.25? Okay, so we're out here pretty darn far, right? So if we look that up in that table, go to the 2.2 row and go over to the 0.5, we come up with 98.78%. Yeah, that makes sense to the table too, doesn't it? That says only really 1% of the students are over here. Yeah, okay, it's a hard test. How do you do that in Excel? Here's one way. You could have also put 91 and put 73 here and 8 there, and it would have done the same thing. All right, so now what's the next question? Let's see what they're saying. just by looking at it, we can tell, oh, well, what's the probability, what's the percentage of students that scored between 89 and 65, although I wrote this backwards in, no, I didn't, I got it right, yeah, so I've already solved it there, yeah, okay. So here, well, yeah. You can see by just what I've done, what it is. So here's our distribution, we are 73. So now we want to know what's the probability that I'm between 89 and 65, okay? So again, we're going to have to subtract that one from the bigger one. Okay, so the probability, 65, our score, 89. Well, we got to put that into the Z world, right? That's like asking what's the probability of 65 minus 73 over 8. Z, that's then 89 minus 73. Okay, so that's the probability of, that one was nice for it, right? Minus 1. And this one was less than 1. That's 16. Yeah, so that was 2. Yeah, that's right. So again, we could go to the table, or we could go to Excel. 97% minus 15. Oh, hey, that was that number we had last problem, wasn't it? Okay, it's 81%, right? This is the probability that Z is less than 2, minus the probability that Z is less than minus 1, and so that was 84%. Does that look right? Yeah, because in the Z world, we're down here. This is minus 1, and this is plus 2. This is sort of further out maybe than I drew it. So that says that in the middle here, that's 81% of the students. Yeah, that's probably right. Yeah, average is 73, and down here 1 standard deviation, 2 standard deviations. Yeah, that got almost everybody, didn't it? Yeah, that's what I think. There's a few really bad students, a few really good students. Right?
So you said a minute ago that putting it in Excel, because right now you're showing converting it to Z world.
Z, I did, yeah.
Using the
Yeah, we could have just
mean and
done.
standard deviation.
Yeah, we could have just done like this, right? Let's see, let's try it. Make sure I'm not lying. There it is, equal. Yeah, so it should have been, we should be able to put in the X value. So let's see, we'll work that one of 89, right? 89, and then we could put in our mean, which was 73, and our standard deviation, which was 8. And we want the sum, and let's see if that just gives us that first number. So that gives you 9, yeah. So that gave you this. Right. So you don't even have to convert it to Z. I converted it to Z because I wanted to, I guess I wasn't really thinking, I was really thinking about, well, how do I relate it to the hand solution I did? Yeah, it's not even, so even using Excel, it's even less hard. Yeah. Because that's what it's doing, you know, it's got the standard normal table built in, and when you type that in, it converts it to it and does it and converts it back to it. So yeah, so it's even easier, right? So yeah, so for the next problem, they're just going backwards now, right? They're saying, hey, what score? Yeah, so here, what score out here, way out here, what's the score here, Z star, where we've only got a mere 5% of the geniuses out there, right? Yeah. And so therefore that means this entire glob area over here is 95%. Okay, so if we're trying to use the table, that's how we would do it. In Excel, we didn't have to. So that says Z star is 1.65. And all the magic again, they're messing with your brain. You won't have that memorized by the end of this class. 1.65, but that's not good enough. That's our Z star answer. We got to put it back into our X world, our score world. So remember here, our score, which is X, is mu plus Z times C. So it's 73 plus Z was 1.65, 8. We get a score of what, 86. 66.2. So again, it's pretty hard test, right? Mean was 73, the standard deviation is 8, so top 5% of the students were in the the 87 was in the top 5%, not a bad score, you know, and you might have thought, 87, that's terrible, I don't like that score, it's not bad for this test. Okay, and so what's the D question? Oh, the D question is, so you got, the professor set it up where, you got one of these options, drop this test or take the other one. So here's your option, you scored an 81, the professor's going to give the top 10% of the people an A on every test. So you scored an 81 on this test, but in the future you scored a 68 on a test where the average was 62 and the standard deviation was 3. Which one are you going to keep? Which one are you going to drop? You know, in other words, with an 81 on this test, are you in the top 10%? With a 68 on that other test where the average was 62, are you in the top 10%? Okay. So let's see. What's one way to answer it? It's the way I did here. Another way to answer it is probably easier to visualize. Let me show you the easier to visualize way first, and then we'll look at that way. If I just look at my standard normalized distribution, I put it in the pen and go back and get my better one. Look at my standard normalized distribution. What are we asking? We're asking, hey, what's the Z out here where this is 10%? That's all we're asking. How many standard deviations away from top 10%? Okay. Well, let's see. Let's see. We can go to the table. Maybe it's the easiest way. We'll do it on here for once. Let's do it here. Let's see. Where are we? 10%. In other words, where are we with 90% of them below us? Here we are, all right. Close enough here and here. Yeah. 1.68, is that right? Let's see. 1.28, is that where we are? Yeah. There. Yeah, right there. Yeah, 1.28. This is 1.28. Okay, so that says if you get a Z-score of 1.28 or greater, you're in the top 10% based on the standardized normal distribution. Well, let's just do that. Okay, the first test, my Z on option number 1 was what I had, 80, well, this thing was away, 80 something. I can't remember now. I can remember. You got an 81. So we get an 81 minus